And we need both of them. In some cases we need an average, in some cases, in some other cases we need RMS. And the idea is this one. What is important is that the power, the dissipated power as a function of time for any component equals the voltage across the component times the current through the component. This is easy. Just P equals V times time. This is the instantaneous power. Power is related to heat. And heat cannot change very fast in any object, any physical object, because there is a thermal capacitance. Any object from the thermal point of view looks like a low-pass filter. That's like a capacitance. And so, what is important to find out the temperature most of the time is the average power. So, we need to find the average power that is dissipated, is generated by a component. And the average power equals, check the time. Più momento. 50 minutes.
Si è già fermato.
Oh, okay. P, average power equals Vt times It average. May I split this average to say that is equal to the average voltage times average current? You wish, but it's not a good idea. So, in order to find the P average, we have to write down the standard equation for average values. Then we will forget this equation because I started to show you how to find the average for waveforms last time, but here I need some math. So I can average over one switching period, because our system is periodic, etc. Integral from 0 to T switch over Vt times It integrated in dt. And here we have two different situations, two different kind of components. For example, we can have a diode. A diode has a current ID that flows through the diode and has a voltage Vd across it. If we want to find out how much power is lost on the diode, how much power is dissipated on the diode, what should we do? Well, we can make an approximation, good, useful approximation, and the approximation is how much is the voltage across the diode when it conducts? More or less, I don't want the complete equation with exponential and something else.
0.6, 1 volt. 0.6,
0.7 volts. Okay, tell me two things, please. First, tell me it's almost constant. And second, forget in this class 0.6, 0.7 volts. Unfortunately, it's not true. For power diodes, the normal voltage across that drops across the diode is as an order of magnitude 1 volt. You can assume 1 volt is a good choice. If it is a normal PN diode, silicon diode. If it is a Schottky diode, what's a Schottky junction? Metal semiconductor. If it is a Schottky diode, the voltage drop is lower. What is the voltage drop for a Schottky diode in signal domain? Signal 0.1, 0.2 volts, even less. Well, in power electronics, when we use a large current, many amps Schottky diode, the voltage drop across the diode is in the order of half volt or so, 0.5 volts or so. That is a good choice. There are other diodes like silicon carbide diode. Did you see the silicon carbide semiconductor? No? Yes? Who knows? Well, silicon carbide semiconductor, silicon carbide has a very good property that it can work at very high temperature in a good way. It's very fast because the silicon carbide diode is basically a Schottky diode. And Schottky diodes are damn fast. There is no minority charges in Schottky diode. But unfortunately, a silicon carbide diode has a direct drop, a voltage drop in the order of 2 volts. You can have everything from your life. You have Schottky diode that works at 600 volts or 1000 volts, but it drops 2 volts. Oh, too bad. If you have a transistor, bipolar transistor or an IGBT, when you saturate it, the voltage drop across a saturated transistor, VCE set, is almost constant. The VCE set for an IGBT is constant, could be a couple of volts or so. So there is a class of transistors, of devices that have almost constant voltage drop. And we can call this voltage drop as VD, capital, constant. And so you see that if you evaluate the average power dissipated by this diode using a constant voltage, this VD becomes capital VD. What happens if you have a constant inside an integral? You walk away from the integral and you get something like VD times, what are you left with? 1 over the switch, integral from 0 to the switch of ID. T, what is this? It's the definition of average. Times ID average. So we need the average current most of the time for diodes, BJTs, IGBTs, and when we need to find out how much is the DC current going into your converter coming out from the converter. What if instead of having a diode, we have something that looks like a resistor? Resistance, not a resistor, sorry. What if our component looks like resistance? For example, the wire of your inductance. The wire of your inductance is a resistance, has a resistance. An MOS transistor is basically a device that when it's on, it's hardly on, looks like a resistance. That is the important parameter of an MOS transistor. So, if you want to find out how much power is lost across a resistance, well, same story. 1 over the switch, integral from 0 to the switch. This is circuit theory, you had it in the second year probably. So, V T times IT by dt equals 1 over the switch, integral from 0 to the switch. How much is the voltage across a resistance? V equals R times I. So we have here R times IT squared by dt. And this is the R moves out from the integral as usual, and we get the average power, the average for a resistor equals R times, I want to write here I square, because Ri square is what I need to get the power. But what kind of curve should I use over here to get the average power? Well, R moves out, and I get the average of square. And this is called RMS. RMS stands for S square. First the square, then I take the average, here it is, and then I take the square root. RMS is just the square root of this. RMS is just a recipe. RMS is just a recipe. RMS of a quantity means take this quantity, square it, average it, and take the square root. This is what RMS means. Just do this, do that, do that. Do this is square it, average it, and take the square root. Then in many cases you have to square it again. So in many cases we will stop at this point. We want to take the square root because quite often we have to square it again. But this is the definition of RMS. By the way, please notice this. I take RMS current. I evaluate the power using an RMS current, and I get power. I get the average power. There is no such a thing like RMS power. Too bad. not my fault. In many cases, you hear, oh, 100 watts RMS. That is bullshit for two reasons. First, power, RMS power is meaningless. What is important is the average power, or the peak power, let's say average power. Second, RMS watts don't exist. There are watts, not watt peak, watt RMS, and so on, like voltage. You can have 2 volts, and this voltage can be an peak voltage, could be an average voltage could be an RMS voltage, but there is not 2 volts RMS, 2 volts average, 2 volts peak. Volts are volts, period. How tall are you?
180. As a 1 meter. 1.8 meters.
1.8 meters. How long is this desk? 2.5 meters. Well, he's tall, 1.8 meters. This is long, 2.5 meters. There is no the meters to measure the distance in vertical, the meters to measure the distance in horizontal. There are no the horizontal meters and the vertical meters. You don't say, I am 1.8 vertical meter tall, or this desk is 2.5 meter wide. Meters are meters, exactly like volts are volts. It's the voltage that can be RMS, peak, average, whatever you want. Anyway, this is the reason why we need RMS current. RMS is applied every time we have something like a resistor. It means in any winding, inductors, transformers, the wire looks like a resistance, has a resistance, and in MOS transistors. An MOS transistor, when it's with the channel is completely formed, is a full conduction, looks like a resistance. Very small value, but it's a resistance. So we need both RMS and average current. Peak is easy. Peak we already have. Let's see. I could stop at this point on this stuff, but I want you to be engineers, not physicists or mathematicians or other things. Engineers are people who know how to make calculations, how to make approximate calculations, how to make estimates, etc. So I want to go a little bit into the details on how to find RMS and average currents. What's this? What's this? Okay, not very meaningful. Okay, let's suppose that we have something like this. This is I1, this is I2, this is I3. What is this stuff now? No. And you know that if you have to find currents in a node or apply an important rule around about nodes and currents is KCL. KCL that tells you that the summation of all currents into a node equals 0. Be careful to the sign, because all currents must be all going into the node or coming out into the node. This equation is not applying to these signs, current signs. We should put I1 coming out. This is the right. What I can you use in this equation? What kind of current can you use in KCL? Well, I can be the instantaneous, that means summation of IT by IT, time domain. Each single instant must have this summation equal to 0. Or, let's see what happens if we take the average of this equation. If I average over here and average over here, is it okay, mathematically speaking? Sure. What is the average of 0? Well, that's difficult. And here we have the average of summation. Average and summation are linear operators. This summation is a finite summation, it's not going to infinity. So, if you have two linear operators, and there is some kind of requirements on the convergence, if you have two linear operators, you can swap them, reverse them. So, this is also equal to summation of I average equals 0. What is summation over I average? You can apply the KCL for averaging current. And we already did it without pointing it out in the text, because when I told you, when I told you, here I have a DC component and an AC component coming out from the inductor. Where is the DC component going to? You got me all through the load. You are applying the KCL to this node for the DC components. So you can separate DC components from AC components. Okay, so this is okay. Let's see if we can extend our KCL a little bit more. Can we use KCL for RMS currents? Let's say, is it true that the summation of I RMS going into a node equals 0? Question mark. No. Why?
Because the square is not a linear.
Because the square, if you make the square, everything becomes positive. Then you integrate, it stays positive. You take the square root, it is still positive. And if you add many positive numbers, you get not 0 for sure. Okay, that is okay. That is really a bad idea. Don't do it. And it's a bad idea because you should say, I apply the RMS operator to summation of I equals 0. RMS of 0 is 0. But RMS and summation cannot swap this time because RMS is a non-linear operator. So you cannot swap with summation. That is a really bad idea. Ouch. But I would like to use something similar to the RMS, to use a sort of KCL for RMS points. Why? Because let's go to see what kind of waveforms we have on our buck converter. The same story applies to all other converters, CCM, DCM, whatever you have. Let's consider, for example, the inductor current. Inductor current is something like this. Or let's consider, for example, the IC in, the input capacitor current. Input capacitor current is something like this. It's just the switch current minus its DC component, minus its DC value. I need RMS, because this tells me the stress on the wire, how much power I lose on the wire. I need IC in RMS, because the RMS current flowing through a capacitor is what is carrying the capacitor. It's what is stressing the capacitor. It's a very important parameter. And, finding out the RMS of this value, this waveform, means what is RMS standing for? S square root M. If you want to write analytically this segment, well, you can do. Then you have to write this segment You will never remember how to write down the equation of a straight line and passing through 2 points without deriving it. And then you have to square it, you have to take the integral. Probability of error is 1.2, 1.3, something like this. Standard probabilities don't go from, only go from 0 to 1, but in this case it's 1.2, 1.3 because there is the Murphy's effect kicking in. So, I would really like to add RMS values like in KCL, but it's not possible because RMS is nonlinear. Here, even worse, if you want to find out the RMS value of this waveform, that's hard. It's hard because you have to write down this sector, this part of this segment, and you have to square it, you have to integrate it, etc. It's just wasting time, a lot of time. There is something better. And the something better is something like this. Let's consider a current, I function of time, that is equal to a DC component plus an AC component. IDC plus IAC function of time. Many of our waveforms are in this form. Have a total current that has DC component and AC component. Have a total current, it has a DC component, I naught in the case of a buck converter, and the ripple on top of it that is the AC component. AC component has an average value that is 0. Remember that IAC function of time average equals 0. This is AC, just AC. I removed the DC part. So what happens if I try to find out the RMS value of this current? RMS value of this current equals what I'm telling you now is nothing new, it's just a way to make faster and safer calculations without having to write down every time equations and deriving expressions, etc. So, if I want the RMS value of my IT, let's say RMS squared because we will just take the square root at the end, but I don't need it right now, equals 1 over this switch, integral from 0 to this switch. This is the only day, the only lecture where I use a lot of integrals. Everything else will be just basic calculations. Integral from 0 to this switch of what? Of IT squared. That means IDC plus IAC function of time squared by dt. And this is equal to, you remember how to make the square of binomial expression? A plus b squared equals a squared plus twice ab plus b squared. Okay, equals 1 over the switch, integral from 0 to the switch of IDC squared by dt. Then we just split the integral in 3 terms because it's something that is legal. Over plus 1 over the switch integral of twice IDC times IAC function of time by dt plus 1 over the switch integral from 0 to the switch of IAC squared by dt. Why am I deriving this expression? Well, I want to give you a sort of KCL for RMS values that is very helpful in working with the switch mode converters. And I'm proving it because I don't want to give you just the recipe. Do this, don't test why. I want to explain you why. So, probably I get 2 advantages that is just in my dreams. First, it will stay better in your memory, and second is a method that you can apply also in your professional life outside of this class. In 2 or 3 months after the exam, you will be allowed to forget everything, but if you don't, it's better. If you forget power electronics, it's okay. Who cares? Unless you go to work in power electronics field. But if you remember some calculation techniques that can be applied everywhere you go, that could be helpful. By the way, there are, I keep getting a lot of, not a lot, but 2 or 3 requests every year saying, I didn't attend your class on power electronics, but now I need it. Can you help me please with this? I say, no, because if you want power electronics, take your class. But I can, even after you are outside the Polytechnic, you can still access the material for classes over here. For example, this recording, this taping, is also used by a couple of people that graduated a few years ago, and they need power electronics. So they are taking the class using their original student ID number, and it's helpful, not for everyone. So, let's see. RMS value of IT squared. Taking, well, it's not RMS squared, means just MS, but it's called RMS in any case. And this IT is made of a DC component plus an AC component. And so we get what? Equals. What is the first integral we wrote on that letter? It's IDC squared integrated from 0 to the switch. IDC is a constant. It moves out from the integral. And so the first term is just IDC squared plus, what about the second integral? IDC times IAC integrated over one cycle. 0. Why? Because IDC is a constant, moves out from the integral, and you have the average value of IAC, that is 0 by definition, because it's just an AC component. So the second term is 0, and the third term is integral of IC squared from 0 to the switch, etc. This is just the RMS value of the AC component. So this is IAC RMS, but this RMS applies only to the AC component, and this is squared. So we still have a sort of KCL. We have I total. Total means AC plus DC. Total means AC plus DC. RMS squared equals IDC squared plus IAC RMS, only the RMS value squared. Well, better than nothing. I like it. And you can also use this equation the other way around. That means we can find, for example, IAC RMS squared. When do we need the AC RMS component for Q? Capacitors. In the capacitor, we have no DC component flowing through it. We have only the AC component flowing through it. So this is typically what we can do for capacitors. Equals I total RMS squared minus IDC squared. This is a possible use of our case, sort of KCL for RMS value. Let's call it quadratic KCL. There is nothing new, it's just a technique to make calculation without wasting too much time. Okay, so far so good? Good. So, did you have classes on numerical analysis or things like this? Calculus numerical? Yeah. You remember what is numerical cancellation?
Yeah.
Okay, we will meet the numerical cancellation in a moment. Let's suppose to have here the output side of a buck converter working CCM So we have IL, it is something like this. This is IL. We have IAC, that is the current flowing through the capacitor. And we have IDC or I naught, that is the current flowing through the load. The average value of the inductor current, this is I naught. The average value of the inductor current flows completely totally to the load. What about the AC component of this current? The AC component, IAC, is something like this. What about the AC component? Does the AC component flow completely, totally, fully through the capacitor? And no, because the output current, the AC component, here finds two possible paths, one through the capacitor, one through here, and it divides. Well, part of the current goes through the capacitor, part of the current goes to the load, unfortunately. But we will take a capacitor, an output capacitor, that has an impedance far smaller than the output resistance. So the AC component mainly flows, 91% or so flows to the output capacitor. The output capacitor will have some ripple, some voltage ripple across it. The output voltage will be absolutely ideally constant, etc. We'll have some ripple on top of it. And this ripple is controlled by the output capacitor. The output capacitor will be chosen to control the output ripple. Okay. How much is I naught? I naught is this. I naught is equal to V out over V out over R or L. That's easy. This is the DC component equal to IDC. Now I would like to find the RMS value for this current and the RMS value for this current, because both of them are important. Which one is easier to evaluate? Which RMS value is easier to evaluate? This red or the white one? White. White means that we have to take this segment, write down the equation for this segment, then we have to and square it. And this segment has an equation that is something like AX plus B. And then we have to write down a different segment. Okay, see you tomorrow when you get to this result. It's far easier to find, in this case, the RMS value for this waveform, the red waveform. Let me just expand a little bit of here. IAC. I exaggerate just to make it easier to see. And this peak-to-peak value, this is the peak-to-peak value of current flowing through the capacitor. Is delta IL that we found 1 hour ago. Now we have to apply the RMS recipe to this waveform. What is the RMS recipe? First thing to do to find the RMS of a function? Square it. Oh, this is a straight line. When you square a straight line, this is a straight line that starts from here and goes up. When you square a straight line, what do you get? X squared gives you x squared, parabola. So that will be parabola like this, starting from with the zero derivative and going up. And what about here? It comes down, like here, and then it comes up, comes here. How much much is the peak value of this strange parabolic triangle? How much is this height? This value, this peak value?
The square of the...
It's the square of this. That is, how much is this peak value? Peak to peak is delta L. Peak value is delta L over 2. So this peak value is delta IL over 4 and delta L is squared. Okay, we square. Second part, the second step in our RMS recipe is S average. Sorry, M. What is the second example? Mean average. So we have to take this area and spread it over one side. Or we have to take this area and spread it over one side. What shape is this? It's a parabolic triangle. How much is the area of a parabolic triangle?
2/3 base is right.
It's 2/3 is the fat triangle, it's 1/3 is the skin triangle. So this area equals this base from here to here, or this base from here to here. Those triangles are exactly all the same. From here to here, at this base times height divided by 3. Height is delta IL squared over 3 over 4, sorry, because it's 2 is delta L over 2 squared, and still divided by 3. This is the area. Then you have to spread this area over one half cycle in this case, or one cycle. If we take one cycle, we have to take twice this value, then it will be long. If I spread this over this base, I have to divide by the base again. And so, without integrals, we find out that AC RMS squared. Oh, the waveform should be something like this. It's a triangle with a zero value. Equals delta IR squared over 12. Because a 4 factor comes from the delta L over 2 squared, and the other 3 factor comes from the integral of a parabolic triangle. That's it. If you try to write down the equations for straight lines passing through 2 points, square them, and find it, you become homogeneous. Okay? So we have IEC squared RMS. We can take a pause, right now, and then 5 minutes, and then we go on. Do you have a calculator with you? Pocket calculator? Yeah, better you have it. But if you don't have it, it's fine. You can use your head. Your head is far more powerful than a pocket calculator. Okay, let's take a break.